In this video, we are going to start by looking at how we can combine vectors. And so we're going to start with a really simple example where we're adding two vectors together. So if I look at two vectors, the vector 1, 2, 3, and I'm adding to that the vector 8, 10, 12, when I can just add them entry by entry. So I get 1 plus 8 is 9, 2 plus 10 is 12, 3 plus 12 is 15. So I get 9, 12, 15. So when we're adding, you just add entry by entry. And what this tells me is I can build the vector 9, 12, 15 out of the vectors 1, 2, 3, and 8, 10, 12. I can build them just by adding those first two vectors together. But I could also look at another example. Let's look at 1, 2, 3, and 4, 5, 6. And I'm looking at these two vectors, and I want to say, can I build the vector 3, 4, 5? And obviously, adding them together won't work. I can't do a subtraction to make them work. I can't make that happen that easily. What I can do, though, is I can say, well, let's take A times the first vector plus B times the second vector and say, can I make that equal C times the third vector? So are there three scalars, A, B, and C, where I can make this equation true? And if so, then I can build that third vector, 3, 4, 5, out of the first two vectors. And you might say, well, wait a second, I can't build the third vector. I can build C times the third vector. But if this equation is true, then I can divide by C and get a way to add these first two vectors together to get the third vector. And so in this case, if I can find A, B, and C where this works, then this is a way to build 3, 4, 5 out of 1, 2, 3, and 4, 5, 6. And so when we are building these vectors like this, we call this where we multiply a scalar times a vector and then add it to a multiple of a scalar times a vector. We call that a linear combination. So we introduced the idea of a linear combination in the last video. We talked about it just a little bit, but it's linear because I'm not using any powers. It's all just to the first power. So I'm building some kind of what we call a linear combination. And so if I'm building this linear combination, I can say, okay, well, what values could I possibly use? And so I could use A equals 1. So I just get 1, 2, 3. Plus B equals 2. Equals, if I set C equal to 3, I get 3, 4, 5. And this turns out now with A equal 1, B equal 2, C equal 3 to be the same as our original question. So now I've found a way that I could build that vector from the first two. But let's take this equation and let's add -3 times 3, 4, 5 to both sides of the equal sign. Because if I do it to the left side and I do it to the right side, then I will get the same, I won't be changing the equality. So if I do that, I get 1, 2, 3 plus 2 times 4, 5, 6 plus a -3, or I could write it as minus 3 times 3, 4, 5 is equal to 3 times 3, 4, 5 minus 3 times 3, 4, 5. And I want to think about what this what the right-hand side of this equation, what that is. So if I were to think about how I could rewrite this, I could write this as this is equal to 3 minus 3 times 3, 4, 5. And 3 minus 3 I know is 0. And if I multiply a 0 times a vector, I'm going to end up with a vector with all zeros, because 3 times 0 is 0, 4 times 0 is 0, and 5 times 0 is 0. So what I end up with is 1, 2, 3 plus 2 times 4, 5, 6 minus 3 times 3, 4, 5 is equal to 0, 0, 0. So that is to say that the three vectors, 1, 2, 3, 4, 5, 6, and 3, 4, 5, I can find a linear combination of those three vectors that gives me an all zero vector. We usually use a shortcut to write the all zero vector. We just write a 0 with an arrow over the top, or a bold 0 to say this is a zero vector, a vector with all the entries equal to 0. And how many entries are there? Well, we use this to represent any of these vectors, so however many makes the question make sense. So in this case, since all the other vectors had 3 entries, the 0 vector would have 3 entries. But what this gives me is that I can combine, I can build a linear combination of 1, 2, 3, 4, 5, 6, and 3, 4, 5. I can build a linear combination of those vectors that is the 0 vector. And so if I can build a linear combination of vectors and get the 0 vector, we say that that set of vectors are linearly dependent. They are linearly dependent because I can combine them together in some kind of a linear combination and get the 0 vector. Or thought of another way, I can combine all but one of them together to get the final one. So one of them can be built from the others through a linear combination. They're linearly dependent. If I can't, if there is no linear combination, well, there's always a linear combination that gives me the 0 vector. But if there is no linear combination other than the trivial one, what do we mean by the trivial one? Well, we mean multiplying every vector by 0. But if I can't build the 0 vector other than by just zeroing everything out, so if there is no linear combination other than the trivial one that makes a set of vectors be the 0 vector, then that set of vectors is linearly independent. So it's linearly dependent if you can find a way to combine them without just zeroing them out and get the 0 vector, or linearly independent if you can't. So, okay. So, if we want to determine if a set of vectors is linearly dependent or linearly independent, what we're trying to do is we're trying to say, well, let's see if we can find a linear combination of them. So let's do this with an example. 0, 1, 5. 1, 2, 8. And 4, -1, 0. What we want is we want to, if it is linearly dependent, we should be able to find a set of scalars, x1, x2, and x3, such that if I take x1 times 0, 1, 5, plus x2 times 1, 2, 8, plus x3 times 4, -1, 0, and set that equal to 0, 0, 0. If I can find a solution other than x1 equals 0, x2 equals 0, and x3 equals 0, if I can find any other solution, then these are linearly dependent. So let's think about how else we could represent this. This is a linear combination of vectors. We can represent this as a matrix equation. 0, 1, 5, 1, 2, 8, 4, -1, 0, times x1, x2, x3 is equal to 0, 0, 0. So that's the equivalent matrix equation. And we know the steps to solving a matrix equation. To solve the matrix equation, all we have to do is look at the augmented matrix and find the reduced row echelon form. So I'm going to get the augmented matrix is 0, 1, 4, 0, 1, 2, -1, 0, 5, 8, 0, 0, and we're going to find the reduced row echelon form. To do that, the first step that I see, the first obvious step for me, is I'm going to swap or interchange rows 1 and 2. When I do that, I get 1, 2, -1, 0, 0, 1, 4, 0, 5, 8, 0, 0. Now, I want to zero out everything below that leading 1 in the first row. The leading the 0 in the second row, that first column has a 0 in the second row, which means that that's already zeroed out. So I need to replace row 3 with row 3 plus a -5 times row 1. When I do that, I get the first two rows stay the same. 1, 2, -1, 0, 0, 1, 4, 0. Then this becomes -5 times 1 is -5 plus 5 is 0. -5 times 2 is -10 plus 8 is -2. -5 times -1 is 5 plus 0 is 5 and 0. Now I'm ready to move on to the second column, to the next, or rather to the next second row, and I want the leading entry in this to be a 1. It already is, so I'm going to use that row to zero out everything below it. So I'm going to replace row 3 with row 3 plus 2 times row 2. And when I do that, I'm going to get, well, row 1 and 2 stay the same. So I get 1, 2, -1, 0, 0, 1, 4, 0, and 0. 2 times 1 is 2 plus a -2 is 0. 4 times 2 is 8, plus 5 is 13, and 0. Now I want the leading entry in row 3 to be a 0. To do that, I'm going to scale row 3. So I'm going to replace row 3 with 1/13 of row 3. So I'm going to scale it by 1/13, which gives me 1, 2, -1, 0, 0, 1, 4, 0, 0, 0, 1, 0. Now I'm going to, for each of my pivots, I'm going to zero out everything above those pivots in the columns. So I'm going to first replace row 1 with row 1 plus -2 times row 2, which gives me 1. -2 times 1 is -2, plus 2 is 0. -2 times 4 is -8, plus a -1 is -9, 0. The second row stays the same, and the third row stays the same. And now I just need to zero out the last column above the last pivot. So I need to zero out the third column in row 1 and row 2. To do that, I take row 1 and I replace it with row 1 plus 9 times row 3, and row 2 becomes row 2 plus a -4 times row 3, which gives me 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0. From this, I can read off that my x1, x2, x3 are all equal to 0, which means that the only solution is the trivial one where they are all zeros. Which means that these vectors, so since the only solution is all zeros, or I could write that as it is the 0 vector. These vectors are linearly independent. So we now have a method to figure out whether a set of vectors is linearly dependent or linearly independent. Let's look at an example of what happens if you try to use this on a linearly dependent set instead. So here's a set of vectors. And this set of vectors is linearly dependent. I know it's linearly dependent because I built this set of vectors by writing down the first two and then writing the third one is 2 times the first one plus the second one. So I know that these have to be linearly dependent. But let's see what happens if I try to figure out whether they're linearly dependent or independent by just using the matrix equation. So the matrix equation would look like 1, 1, 3, 1, 1, 3, 0, 2, 2 times x1, x2, x3 is equal to 0, 0, 0. If I write this out as a augmented matrix, I get 1, 1, 3, 0, 1, 1, 3, 0, 0, 2, 2, 0. and I try to find reduced row echelon form in that. So I've already got my leading coefficient in my first row is a 1. So I'm going to take and use that to clear out the all the numbers below that in the first column. So row 2 is going to become row 2 plus a negative row 1, which gives me 1, 1, 3, 0, 0, 0, 0, 0, 0, 2, 2, 0. Now I'm going to swap rows 2 and 3, which gives me 1, 1, 3, 0, 0, 2, 2, 0, 0, 0, 0, 0. I'm going to scale row 2. So row 2 is going to become 1/2 of row 2, scaling it by 1/2, which gives me 1, 1, 3, 0, 0, 1, 1, 0, 0, 0, 0, 0. Then I have a pivot, and I don't have any non-zero things in the last row, so I don't have to worry about that. So now I have a pivot in the second row. I look at that pivot, and I'm going to zero out everything above it. So I'm going to replace row 1 with row 1 plus negative 1 times row 2. When I do that, I get 1, 0, 2, 0, 0, 1, 1, 0, 0, 0, 0, 0. And that is my reduced row echelon form. So what does that tell me my solutions are? Well, it tells me that x1 plus 2x3 is equal to 0. It tells me that x2 plus x3 is equal to 0. And it doesn't tell me anything else. So I have one free variable, x3 is free. I can set it to anything I want and get another solution. And since I'm getting infinitely many solutions, in particular I can pick x3 equals, let's say, 1. So I can set x3 equal 1. That gives me that x1 plus 2 times x3, 2 times 1, is equal to 0. And x2 plus x3 is 1, is equal to 0. I can find x1 and x2. So x1 equal negative 2, x2 equal negative 1, x3 equal 1 is a solution. And since this is a solution that is not all zeros, I have that that negative 2, negative 1, 1 is a solution that is not the zero vector. So these vectors are linearly dependent. So there's a few shortcuts sometimes to figuring out whether sets are linearly dependent or linearly independent. One of the big ways that one of the quick shortcuts that we have is if our set has a zero vector in the set, then I can always just put a 2 times that or any other number times that and get a non-trivial solution. So any set of vectors containing the zero vector is linearly dependent. Another way that I can think about, another way that I can sometimes find very quick solutions, a very quick way to determine if a set is linearly independent or linearly dependent, is any set of vectors that has more vectors than there are entries in each vector is linearly dependent. So I want to think a little bit about why that's the case. And so if I think about the matrix equation, if I think about this matrix equation, and I have, let's say I've got some values, and let's say I've got maybe there's 4 rows, so in this case my xp is just x3, x4. If I have at least 5 columns, my matrix equation is built from at least 5 vectors, then when I find the reduced row echelon form of my augmented matrix, it at best is going to have a pivot, a pivot, a pivot, a pivot, and then some row that doesn't have a leading whose leading coefficients could be whatever. Their leading coefficients don't have a pivot. And then maybe there's more columns, but if there's more vectors, but then you've got the 0 vector from your solution from this 0 vector. And so this means that the 5th x5 is a free variable, which means that there is a solution other than the trivial solution. And so that is enough to show that these are linearly dependent. And that is everything I wanted to go over in this video. So I will see you guys again next time.